what an analog to digital converter does. You have to evaluate a real-world engineering scenario and specify exactly which ADC or DAC architecture to use when translating the physical world into a format a microcontroller can process. Your selection is governed by 3 parameters. The first is resolution, the system's ability to detect minute fractional changes in physical variables. The second is speed, which dictates the sampling rate necessary to capture rapid physical events as they happen. The third, often forgotten parameter is isolation. Industrial settings are packed with erratic electrical noise and hazardous voltages. Your converter must reject this interference to protect delicate control electronics. If you blindly choose a chip with the highest resolution or the fastest clock speed, without balancing all 3 of these parameters against the physical environment, your design will fail in the field, and you will fail the exam question. This table breaks down common process scenarios. Let's look at a chemical reactor. Temperature changes very slowly over time, but missing a fraction of a degree in a fluctuation can ruin an entire chemical batch. Because the physical variable moves slowly, a high-speed sampling architecture is entirely unnecessary. Running a converter at excessive speeds here captures unwanted electrical noise, distorting delicate readings. The correct choice is the sigma-delta architecture. It filters interference, providing 16 to 24 bits of resolution, deliberately trading speed for exceptional noise immunity. In process industries like chemical or flow control, engineers intentionally bottleneck the sampling rate to guarantee absolute measurement precision. Now, compare that to an automated robotic arm tasked with high-speed component placement on a circuit board. Here, exact position and force data must be calculated in real time, often in the tens of kilohertz range. The sigma-delta architecture is useless here. Its slow response time would cause the feedback loop to lag behind the physical motors, leading to severe physical instability or equipment crashes. To solve this, we rely on successive approximation, or pipeline ADCs for rapid data acquisition. When paired with a pulse width modulation DAC, the control system can actuate motors swiftly enough to keep pace with the environment. Robotics and automation dictate a strict shift in strategy. Rapid data flow must take priority to maintain physical control over a dynamic, moving machinery. Let's test your baseline. What architecture should you select for a standard programmable logic controller, a system that manages general sensors and valves, requiring a well-rounded balance of speed and accuracy? Lock in your mental choice for both the ADC and DAC before the timer hits 0. The timer hits 0, and the blank spaces flash to reveal SAR ADC and R2R Ladder DAC. The industry standard is the SAR ADC on the input, paired with an R2R Ladder DAC on the output. This combination yields a highly scalable, balanced approach. When an application doesn't demand extreme processing speeds or microscopic resolution, these balanced architectures are your safest default bet. This schematic outlines the most demanding scenario you'll see: medical ultrasound imaging. We are managing high-frequency sound waves where microscopic detail, processing speed, and strict patient safety standards all intersect. In medical diagnostics, signal inaccuracies or electrical leaks lead to incorrect diagnoses and direct physical hazards. This makes extreme low noise and isolation non-negotiable. Notice the path of the signal chain here. The raw analog data is pushed through a low-noise amplifier and an anti-aliasing filter before it is allowed to reach the ADC. This strict front-end arrangement ensures that dangerous signal artifacts and baseline electrical noise are entirely stripped away before any digitization happens. In sensitive medical equipment, the ADC's precision is entirely dependent on the quality of the noise filtering chain that precedes it. Let's lock this in for your exam. Grab a screenshot of this matrix, which maps the physical scenarios directly to their ideal converter architectures. For slow, high-accuracy applications like temperature and chemical flow, you choose sigma-delta. For high-speed motor control in robotics, you switch to SAR, pipeline, and PWM. Mastering control engineering comes down to exactly this: